In this video, we'll discuss some spectroscopic properties of amino acids. Now, this is not going to be an in-depth video by any means. It's just going to give you an idea of if you were to do some research with amino acids or some proteins, how would you, use spectroscopic techniques to identify different features of your proteins or amino acids, okay? So all amino acids absorb in the IR, so you can use IR to get an idea of that. So phenylalanine, tyrosine, and tryptophan absorb in the UV. So absorbance at 280 is good for amino acids or for proteins in order to get a rough quantitative analysis of proteins. NMR is used to characterize each residue in a protein. And high-resolution NMR can be used to elucidate three-dimensional structures of proteins, especially if you have a specialty NMR, which a lot of the really large schools may have a specialty NMR that has something like magic angle NMR, where proteins can be elucidated in a better. You can get the three-dimensional structure. But most places don't have that advanced equipment, and so they'll be limited to some more rudimentary techniques. Okay, so the measurement of protein solutions at 280 is not strictly quantitative for all proteins, since the assay is based on the strong absorbance of tyrosine and tryptophan. This is for UV. Protein concentrations can also be measured at 214 and 205. So here we have some UV spectra of amino acids at pH 6. Here we have tryptophan and tyrosine. You can see that they absorb at 280. And here we have phenylalanine, which absorbs at around 260. So if most proteins have an average of a certain tryptophan or tyrosine content, then you'll be able to get an average of how much protein you have in your sample simply by doing UV and getting a quantitative measurement of how much of the tryptophan and tyrosine absorb. You can correlate that, especially if you have some standards to go by. Additionally, we could use NMR to determine content of amino acids or to identify amino acids. For example, here we have L-alanine, and so of course we can't distinguish between D and L amino acids specifically in NMR, but we don't really have to worry about that anyway because they're all L. But anyway, so we can see here, remember your NMR techniques. So we're measuring, this is proton NMR, so we're measuring hydrogens, and so this hydrogen on the alpha carbon, remember the N+1 rule, has 3 neighbors, so it's going to give 4 peaks, so that's this peak right here, and its integration will be 1, because it'll be representing 1 hydrogen. Here at 5, we have a singlet for the amines, which we can also see over here in the tyrosine a spectrum, and also we can see our alpha carbon absorbs, gives a signal here at a little over 4, so both of the alpha carbons are around 4. For tyrosine, that alpha carbon hydrogen is a triplet. I meant the hydrogen on the alpha carbon, I'm sorry, is a triplet because it has 2 neighbors. Okay, so back to alanine, this doublet is coming from this CH3 group here because it's being split by this hydrogen, and we're not seeing the carboxylic acid OH, which would be at around 12, which isn't shown on the spectrum. And so actually, if we're at, depending on what pH we're at, you may or may not see that. So for tyrosine, we have the alpha carbon hydrogen again, the amine. We've got the aromatic hydrogens at around 7, and what about 3? We've got these CH2s, okay, and they're in a doublet because they have 1 neighbor here. I don't see the OH for the tyrosine here. Depending on what solvent we're in, we may not see that. Okay, and so, but again, you're not going to have to elucidate these structures unless you're doing research with this or something, I don't think, for this semester. Alright, and so here's a carbon 13. You can see that we get a line for each of the carbons in lysine here, and that line will shift according to what pH we're at. And so carbon 13 works by giving us one signal for each carbon in the spectrum. Alright, thanks for watching. I'll see you in the next video.